Okay, we're going to take a look at trying to calculate the total amount of energy needed to take, let's say, 2 kilograms worth of ice at minus 50 degrees Celsius all the way up to steam, very hot steam, at 120 degrees Celsius. You can see from this particular graph that we're looking at 3 temperature changes. One is what we call the warming up of ice. Then we have the melting of ice. Once the melting is complete, we have the warming up of water. Then we have the complete vaporization or boiling of the water. And then you have nothing left here but gas, and we are going to warm this up even more and get it to 120 degrees worth of steam. That's really hot steam. The bottom line is we have what we call 1, 2, 3 areas where the kinetic energy changes because there's a temperature change. And we have 2 areas, these 2, where there is no kinetic energy change, but there is potential energy change. All right, so in order to answer the question, which is, what's the total amount of energy used to do this for water, for 2 kilograms worth of water? We really have to do 5 calculations, get all the answers in kilojoules, and then add them together. What I'm going to do with you just to get you started is we're going to do the calculation for the warming up of ice and the melting of the ice. So we're going to take it from A to C, and then you guys are going to try to finish off the last 3 sections of the calculation on your own. Then look at my key and compare your work and your final answer. Let's start then with area AB. In order to work out the total amount of energy change happening here, obviously it takes energy to melt ice, well, actually just to warm it up first and then to melt it. So this is the warming process. It takes energy to do that, so that energy is coming from the surroundings. It means that this is an endothermic process. The energy is going into the ice to basically break the bonds between the molecules of water such that the ice will eventually melt right here. Okie dokie, so for AB, we are going to do a Q is equal to MC delta T calculation. It's very straightforward. The delta T is going to be the difference between this and this, which is 50 degrees C. The C is a specific heat capacity of the actual ice. That's a constant. And in order to get that number, we take our handy dandy data table. I've done a little mini one here, just of the ones we need, the constants. And that specific heat capacity of ice is right there, 2.10 kilojoules per kilogram degree C. You will never have to remember these numbers. They'll be on your data table for all the calculations. And then we said that the mass is going to be 2 kilograms. So let's use 2.0 kgs. The specific heat capacity, like I said, is right here. It's going to be 2.10 kilojoules per kilogram degree C. We shut that in. We can see immediately that kilogram and kilogram will cancel. And then we have to multiply it by the delta T. The delta T happens to be the difference between 0 and 50, minus 50. So we use absolute values. It's going to be 50 degrees C. We can then cancel the degree C with that degree C, multiply this by this by this. You will get an answer. And you guys can put that answer here, and it'll be in kJs. So that's for the first section right here. Now we're going to do the second calculation, which would be the total amount of energy required to actually completely melt 2 kilograms worth of ice. So we will talk about BC. Now here's the thing, there's no temperature change, so you can't use Q is equal to MC delta T. What we can do instead is we can look at using a very specific relationship which basically says that the total energy change involved in the melting of 2 kilograms worth of ice is equal to the number of moles of ice that we're using multiplied by a constant known as the molar enthalpy of fusion. And that, my friends, is also a constant, and it's right there. Look at that. It's 6.01, and it's expressed in kilojoules per mole. All right, let's do this one, and then I'm going to leave you guys to finish the last 3. Here we go. We are going to use the amount of ice, which we started with at the beginning, as 2 kilograms. Now you can write this out as 2 kilograms if you like, but bottom line is you have to convert it to grams. So let's get rid of kgs, put g's up there. 10 to the 3 of these are in one of these, that and that will go. We're still working out the number of moles. Now we convert the actual grams to moles. And at this point, we need the molar mass of water. The molar mass of water is actually 18.02. Do you guys remember how to work that out? 0.02. Sorry about that, it's a bit squishy in there. But basically this number comes from the fact that water is H2O. That means you look up the molar mass of hydrogen, you multiply it by 2, and you must also add 16 for the O. When you add these guys together, you get our nice handy dandy 18.02. That's the molar mass of water. You could as well remember that number because we're going to be using it a lot, and the units are always grams per mole. So because we wanted to get rid of grams, we put the grams at the bottom this time and the moles at the top. And then this, we call this this NH right here. This is the heat of fusion. That heat of fusion is 6.01. So we're going to pop 6.01 here, and that's going to be in kilojoules per mole. Mole and mole will then cancel because we'll put brackets around this as well. And look at this, we end up with everything in kilojoules. Now I'm just going to put a little circle around this because that's basically extra information as a bit of a review for you guys. The bottom line is, in order to get the total amount of energy involved in this, you would simply multiply that by 1,000, divide it by that, multiply it by that, and you get a number. You guys can do that part. I don't need to spoon feed you. I know you're smart cookies. So this will give me the total amount of energy involved in the melting of the 2 kilograms worth of ice. All right, now here's where the fun starts. I want you guys to do the CD portion, the DE portion, and the EF. This one, remember, is an MC delta T. This is an MC delta T as well, but this is the MC delta T for water, which means we'll be using the specific capacity of liquid water right there. This is our little data table. You like that? Haha. And then, of course, right here would be the amount of energy required to actually warm up the steam or heat up the steam. So we'll be using the specific capacity of steam, which is right there. This guy, between D and E, will be exactly like this, except that instead of the heat of fusion, that's not melting. Fusion means melting, so that's not melting. It's called vaporization instead, so you'll be using this constant. That's the amount of energy required to actually vaporize 1 mole worth of water. These are all constants for water. They exist for virtually everything out there, but we're just focusing on water for us. Okay, so your job is to actually do the following. You're going to find out the total amount of energy to basically convert the right here, what do we call that little bambino? Ha! You're going to convert, sorry, I'm getting distracted by my puppy. You're going to convert all of the ice that we have here. Ultimately, we have to warm up all the water that we got from the ice all the way to 100. So again, it's a MC delta T question. So it's going to be Q is equal to MC delta T. Go ahead, the delta T becomes 100 because the temperature changes 100. Then you're going to work out the amount of energy involved in actually vaporizing the bambino. There we go. This is going to be an H is equal to NH, but it's for vaporization. And then the last but not least portion of this is to work out the total amount of energy involved in the heating up of the steam. And again, that's going to be a Q is equal to MC delta T as well. But remember, the delta T now is going to be the difference between 100 and 120, so it's only 20 degrees C. The specific capacity is going to be for steam. There it is, it says steam. And then, of course, the mass always stays the same. It's just 2.0 kilograms. So have fun, you guys. You should be able to finish this without much ado. Hope you're well. Talk to you soon.